Good afternoon, everyone. I'm Natalia, and along with my colleague Victor, we welcome you to our presentation on thermodynamics.
Thermodynamics is a fundamental branch of physics that studies the relationships between heat, work, and energy, as well as transformation that systems undergo. This field is essential for understanding a wide range of phenomena of the operation of the engines of the transformation of the stars. We will explain how these concepts are so present in the daily lives and why they are fundamental to understanding this universe.
We are going to define what we understand by temperature and heat and how they differ.
We also explore the history of this concept and the laws that govern them.
Let's get started.
Basic concepts. Can you explain that heat in place, Natalia?
Temperature is a measure of the average kinetic energy of the particles in a system. It tells us how fast the molecules are moving. Therefore, it has different scale units than heat.
Sure, heat is the transfer of thermal energy between two systems or between a system and its environment due to the temperature difference in the inherent of intrinsic. That means that temperature is an intrinsic property of the system, while heat is a process. It's like I say that speed is a property of a car, while the movement is a process of going from one place to another.
Here are the temperature scale units. First, we have Celsius, and that is a scale based on the freezing and boiling points of water. That is 0 Celsius grades and 100. Then we have Fahrenheit, a scale commonly used in the United States, where the freezing point of the water is 32 degrees and the boiling point is 212 degrees. Finally, we have Kelvin, an absolute temperature scale where absolute zero is 0 Kelvin or minus 273.15 Celsius degrees. And this is useful to use in science because it doesn't have negative numbers that mess up calculations. The conversion to Kelvins to Celsius is Celsius degrees plus 273.15.
We have many scale units for heat. The first one is calorie, which is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Then we have kilocalorie, that is equals to 1,000 calories. Then there's a joule, which is the unit of energy in the international system of the units, and has equivalence of 1 calorie equals 4.184 joules. Finally, heat transfer happens in many ways. Combustion. Heat transfer to a material due to temperature difference. Example, heating a metal bar by placing one in the contact with the heat source. Convection. Heat transfer due to the movement of fluid. Example, heating water in a spot where the hot water rises in the cold water sinks. Radiation, heat transfer through electromagnetic waves. An example is heat from the sun rising in the earth. Now, let's talk about the basic principle of the super thermodynamics. Where do we start?
First, the zeroth law of thermodynamics, the thermal equilibrium. Two or more systems are in thermal equilibrium if, when they are brought into contact, there is no net transfer of heat between them.
Does that mean they have the same temperature?
Exactly.
Understood. What else can we know?
Well, we also have the first law of thermodynamics, that is the conservation of energy. In an isolated system, the total energy remains constant.
This second law states that the entropy of the isolated system avoids increase or remains constant in a residual process? In simple terms, the server hours increases.
What is enthalpy exactly?
It's a measure of the disorder or randomness of the system. The greater of the entropy, the lower on the availability of the energy to do work. And the third law,
The third law states that the entropy of a system approaches a minimum value as the temperature approaches absolute zero. At absolute zero, the entropy is zero for a perfect crystal.
and that is so important about the absolute zero.
It is important because it is a lower limit of temperature. Nothing can be below absolute zero.
Well, these laws seem very abstract, but they are fundamental to understand the behavior of the energy and matter.
That is right, Victor. And they apply to everything from car engines to black holes. Well,
Formulas.
the time has come to see some of the most important formulas in thermodynamics.
That seemed like a good idea, Natalia.
Okay, keep going in the presentation. First, we have the relationship between heat and temperature. That is Q equals to mc delta T, where Q is a heat transferred, m is a mass, C is a specific heat, and delta T is a change in temperature.
What is a specific heat?
It is the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius.
Do different substances have different specific heats?
Of course, they have different specific heats. Water, for example, has a very high specific heat, which means it needs a lot of energy to change its temperature.
I understand. What else should we know?
Well, because the zeroth law of thermodynamics means that there is no heat transfer between two systems, then we have to establish that Q1 plus Q2 equals 0.
Then we have the first law of the thermodynamics expressed mathematically, and that is delta U. The change of the internal energy of the system is equal to Q. The net heat added to the system minus W, the net network done by the system.
Now we're going to expand a little in thermal expansion. That is the change in the size of material due to a change in temperature. Equations of thermal expansion. Linear expansion. Linear expansion refers to the change in length of an object when its temperature changes. The formula is delta L equals to alpha times L times delta T. That defines how much an object's length, delta T, changes based on its initial length, L. The temperature change, delta T, and the coefficient of linear expansion, alpha, which is a material-specific property.
Volumetric expansion. Volumetric expansion describes how the volume of the substance changes with the temperature. The formula delta B equals beta B for multiply delta T. Illustrates the concept where delta B is a change of volume, B is an initial volume, delta T is the change in the temperature, and alpha is the coefficient of volumetric expansion, also unique in each material.
Now, let's recap the history of these concepts. The understanding of temperature and heat has evolved over the centuries.
Where are we going to start?
One of the first milestones was the development of thermometers. Galileo Galilei built one of the first thermoscopes in the 16th century. It was a device that showed changes in temperature, but it did not have a standardized scale. Later, in the 17th century, Santorio added a numerical scale to the thermoscope.
Who were to next advance to this field?
Daniel Gabriel Fahrenheit and Anders Celsius were crucial. Fahrenheit introduced his scale in 1724, and Celsius proposed his in 1742. They allowed comparing temperature measurement in different places and time.
And what about the concept of heat?
Initially, it was believed in the caloric theory, an invisible substance that flowed from hot bodies to cold bodies. It was proposed by several scientists, including Antoine Lavoisier. However, this theory has been challenged by the experiments of Benjamin Thomson or Count Rumford in the late 18th century. Tell me, Victor, do you know what Rumford discovered?
Well, Rutherford observed that when drilling cannons, a large amount of heat was produced constantly, which suggested and that heat was not a substance, but a form of energy.
Interesting. Who has contributed to changing our understanding of heat?
James Prescott Joule conducted a K experiment in 16 no 18 14 40 that demonstrated the equivalence between mechanic works of the heat. This led the formulation of the first law of the thermodynamics.
The second law, which introduces the concept of enthalpy, was developed by C.D. Carnot, Rudolf Clausius, and William Thomson, or Lord Kelvin, in the 19th century.
So, of the centuries, we went from invisible substance to a form of the energy of the fundamental laws of the govern the universe.
That is right, Victor. Each of these discoveries built on the previous one, leading us to our current understanding. Okay, now let's talk about some of the people who made our current understanding of temperature and heat possible. First, we have C.D. Carnot, who studied the efficiency of heat engines and laid the foundation of the second law of thermodynamics.
What did he discover?
He demonstrated that the efficiency of a heat engine is limited by the temperature difference between the hot reservoir and the cold reservoir.
James Prescott Joule, who know the key of the experiment that demonstrates the equivalence between mechanic ball and heat. He's worked on the formulation of the first law of thermodynamics. What did he do exactly? He uses the apparatus to convert mechanical work into heat and measure the amount of heat produced. His experiments show that the specific amount of work always produces the same amount of heat.
William Thomson, or Lord Kelvin, developed the absolute temperature scale, known as the Kelvin scale. His scale is fundamental to thermodynamics because it begins at an absolute zero, which is the lower limit of temperature.
Rudolf Celsius introduced the concept of the entropy and formulated the second law of thermodynamics in the terms of entropy. He defined the entropy as a measure of disorder of a system and demonstrated that entropy always increases in an insulated system.
Each of these scientists contributed uniquely to our current understanding of temperature and heat, and their work continues to be relevant today.
Practical applications. Use of thermometers. Thermometers are the fundamental instrument that allows temperature measurement in the different contexts, from medical use to the metallurgy, facilitating monitoring of the heat and weather conditions.
Food cooking and heat transfer. Cooking food involves heat transfer, where temperature is crucial to ensuring food safety and quality. For example, different cooking methods, such as boiling, baking, and frying, require specific temperatures to achieve the desired results. Also, I want to talk a little about some of my experience in baking or cooking, which most people can relate to. When you want to bake something, you have to make sure to preheat the oven for a minimum of 10 minutes, so your food comes out well cooked and in a reasonable amount of time. When you don't do this, it takes much longer to cook and you risk the food sticking to everything. This is because, as we talked about it before, the formula of transferred heat includes the mass of the system. That means the more mass the system has, the more heat it needs to be transferred to achieve a final temperature. So, it is best to heat the oven or the pan empty.
Heating and cooling system. Heating and cooling systems such as air conditioners and radiators use the thermodynamic principle to maintain comfortable temperatures in closed space, adjusting the thermal energy has needed.
Thermodynamic exercises. Um, um, Now we're going to see another practical application visually and apply some of what we have learned today. One of the many practical applications of thermodynamics and thermal expansion is in the industry is filling up bottles of different materials with liquids such as water, juices, or sodas. Because in many cases, the temperature which they are bottling up the beverage is very different to the temperature in which the liquid is consumed. And if this is not considered, the bottle may deform. In this case, we're going to exemplify something that may happen in our daily life, like freezing a 1 liter bottle of water to get a cool beverage for the next day. The question is, how much do I have to fill the bottle so it doesn't deform? Now, we're gonna calculate this by using some data. For example, the beta coefficient for PET is 0.0021 inverted Celsius degree. The initial volume is 1 liter. The initial temperature is 25 degrees Celsius, and the final temperature is minus 18 degrees Celsius. For water, it's a little more complicated because the beta coefficient changes between the temperatures. So we have for 21 degrees Celsius, 207 times 10 to the minus 6, and for 4 degrees Celsius, 2.10 times 10 to the minus 4. The initial volume is the same, is 1 liter. The initial temperature is 25 degrees Celsius, and the final temperature for water will be 0 degrees Celsius because then it turns to ice, and the density also changes. That is why we have to use density heat also, and that is 997 kilograms per cubic meter. For ice, I only found out about the linear coefficient, that is this number right here. So I multiply that by 3 to get beta, which is 1.53 times 10 to the minus 4. Then the initial temperature is 0 degrees Celsius. The final temperature is minus 18. And our density here is 917 kilograms per cubic meter. The method we're gonna use is to first find out how much the PET bottle will expand, or in this case contract, between 25 degrees Celsius to minus 18. And then we're going to measure the same thing for water, but just still 0 degrees Celsius. And we're going to take into account the density, the change in density from water to ice, and multiply it by that value. So we get the initial volume for ice, and then we can calculate finally how much will the ice shrink from 0 degrees Celsius to minus 18, and then we can divide the result of the final volume for PET and the final volume for ice to get how much of, so to get finally how much we have to fill our bottle of water. So we're going to start with the volumetric expansion of PET. As we remember, the formula for volumetric expansion is the beta coefficient times the initial volume times delta T, that in this case will be minus 18 minus 25. This multiplication will have a result of minus 9.03 times 10 to the minus 3 liters. That indicates a contraction in volume. Then to get the final volume, we have to just add the initial volume, that is 1 liter, and that gives us the result of 0.99097 liters. That is equal to 990 milliliters, and that indicates a contraction of nearly, well, more than 10 milliliters. That it is about this much volume that have contracted from the bottle. Well, now that we know that the bottle have contracted a little, we're going to measure how much the water will contract from 25 to 0 degrees Celsius. So first we're going to calculate our beta. We have a simple formula for the average. So that leads to 2.1735 times 3 to the minus 4. That we're gonna use. Now, the initial volume is the same, and the delta T will be minus 25. That leads us to this result. That we're going to add to the initial volume, and as we see, the water has contracted about 6 milliliters of water. So now we have to calculate how much the volume in water will change when the water crystallizes into ice. And for that, we will have to multiply this volume times the result of dividing the density of water to the density of ice. That it leads us to this result of 1.081 liters. That is about this much. We can see this in a glass. It expanded a lot for me. That will be our initial volume for ice. Finally, we're going to measure the tiny but existent volumetric contraction of ice from 0 to minus 18 degrees Celsius. Well, the volumetric expansion of ice is more steady than water, so we're going to use that value times the final volume that the initial volume that we calculated here, times delta T, that gives us minus 2.97 times 3 to the 10 to the minus 3. We're going to add the initial volume, and that gives us finally 1.078 liters of of ice. It just contracted very few milliliters, and finally we just going to divide the final volume of PET to the final volume of ice. That gives us a result of 91.9%. That equals to 919 milliliters of water. That is our final answer. So what we get from this practice is that we have to fill the bottle about 90% of the volume of the bottle of water of plastic. That it will be just about here. We can finally put this in the freezer thanks to thermodynamics.